Alright, so today we are going to be talking about these things called rational expressions. In fact, we're going to be talking about them pretty much for the whole week. Okay, so let's start by what is a rational expression? Well, a rational expression is simply just a fraction. Now, we've been seeing fractions for pretty much our entire mathematical career at this point. Alright, but now we're going to be looking at them at a little bit more in depth. A rational expression is a fraction that contains a variable. So some simple ones would be something like x plus 1 all over, let's say, x minus 3. Or more complicated expressions like x squared plus 3x plus 4 over x squared minus 9. Okay, these are all rational expressions. Now, if you came through our courses here at CCAC, you started looking at these in your Math 90 class. And of course, depending on who you had in your Math 108 course, you may or may not have covered these. As with any fractions, rational expressions should also be in lowest terms. It is improper to cancel out the x and the x squared here. In order to reduce or write these rational expressions in lowest terms, the key is going to be to factor. So before we get into that, let's lay out some keys to success. When simplifying rational expressions, the keys to success are to first make sure your polynomials in both the numerator and the denominator are in descending order. So descending order, again, that means starting with the highest powered exponent and decreasing by 1 or 2 each the way down. So it should be the highest powered exponent, then the next highest, next, so on and so forth, until you get down to your constant term. The second key to success I'm going to impart on you is to make sure that the leading coefficient is positive. It's much easier to factor if the leading coefficient is positive. So if necessary, you may need to factor out a -1. And of course, the key to this section is going to be to factor. Factor. So if need be, you might need to review one of the appendixes in the back of your text to review your keys on factoring. Okay. So let's think back. I said a rational expression was simply just a fraction. So how would we simplify fractions? Well, the way in which I teach my Math 80, Math 90 students to reduce fractions is to use the prime factorizations of each number. So for this first fraction, I have 42 over 54. I'm going to use the prime factorization for each one of these numbers and write it down. Now, to get the prime factorization of 42, the way in which you can do this is to factor down 42 using a factor tree. Now, as you may recall, factor trees themselves are not unique. However, the end result, the prime factorization, is. So the prime factorization for 42 is 2 times 3 times 7. Now we're going to do the same thing here with 54. 54 factors into 6 and 9, 6 factors into 2 and 3, 9 factors into 3 and 3. So the prime factorization for 54 is 2 times 3 times 3 times 3. Yes, I am well aware you can write this using an exponent, but this is what we call expanded form, and it's actually going to help us here in what we're trying to build from. Now, to see that, to make sure these fractions are in lowest terms, we're going to cross out what appears in both the numerator and the denominator. Now, mind you, it is a 1-to-1 correspondence. So for every 1 in the numerator, you can only cancel out 1 in the denominator. So clearly, you can see we can go ahead, cancel out the 2's here, and also cancel out the 3's. This then leaves me the final fraction of 7 over 9 when I multiply what's remaining across. All I have left in the numerator is a 7, and then 3 times 3 gives me the 9. So 42 over 54 is an equivalent fraction to 7 over 9. All right, they're equivalent fractions. They represent the same value. This one, though, is in lowest terms. In other words, there's no common factors between the numerator and the denominator. Just said something interesting there. There's no common factors between the numerator and the denominator. So as I had said earlier, the key to rational expressions is going to be to factor. So let's look at the first example I have for us today. The first example here of a rational expression I have is x squared over 4 all over x squared plus 6x plus 8. The key here is going to be to factor the numerator and the denominator. So using all the factor rules that we've been talking about over the last few semesters, x squared minus 4 is a difference of squares. So that's going to factor into x plus 2 times x minus 2. And in the denominator, I have x squared plus 6x plus 8. That'll go ahead and factor into x plus 4 and x plus 2. Like the normal fraction we had just got done talking about, okay, we look to see if there's any common binomial factors in common. As you can see here, I have an x plus 2 and an x plus 2. These will go ahead and cancel each other out. This will then leave me x minus 2 over x plus 4. Okay. Now remember, x minus 2 represents a single number and x plus 4 represents a single number. Therefore, we're not able to cancel out the x's or reduce down the 2 over 4. So x squared minus 4 all over x squared plus 6x plus 8 is an equivalent fraction to x minus 2 over x plus 4. This one, though, is in lowest terms. Let's look at a second example. In the next example, I'm looking at x squared plus 7x plus 10 all over x squared plus 13x plus 40. Again, just like in the last example, we're going to go ahead, factor the numerator and the denominator. So x squared plus 7x plus 10, that'll go ahead and factor into x plus 2 times x plus 5. And then in the denominator, x squared plus 13x plus 40, that's going to go ahead and factor into x plus 5 and x plus 8. Okay? Again, we look for common binomial factors between the numerator and the denominator. As you can see, the x minus 5 isn't common. So this rational expression reduces down to x plus 2 over x plus 8. Okay. Wonderful. Let's look at the next one. In example 3, I have 9x squared minus 1 all over 6x squared minus 5x plus 1. Again, in looking at this, we like to go ahead and factor these expressions down. 9x squared minus 1 is a difference of squares. That'll go ahead and factor into 3x minus 1 times 3x minus 1. In the denominator, you would go ahead and use the aside technique, or at least what I call the aside technique. We have a leading coefficient of something other than 1, and that's why we'd have to use it. When you do, you'll find this factors into 3x minus 1 times 2x minus 1. In looking at this expression, again, we're looking to see what is in common. In common here, I have the 3x minus 1, so they'll go ahead and cancel out. This then leaves me 3x minus 1 over 2x minus 1. And this fraction is now in lowest terms. All right, I got 2 more for you. In example 4, I'm looking at x cubed plus 1 all over 4x squared plus 3x plus 1. Okay. Now, in the numerator, this is a perfect cube. So we're going to go ahead and factor it. Perfect cubes factor into a binomial times a trinomial. The terms of the binomial will be an x and a 1. As you recall, the terms of the trinomial are built from the terms of the binomial. We're going to go ahead, to get the first term of the trinomial, we're going to square the first term of the binomial. To get the middle term, we're going to multiply these two terms together. So 1 times x will give us x. Squaring the last term of the binomial, 1 squared is then 1. And then, of course, for those of you that had had me before, you remember my infamous saying, SOAP. It helps us determine the signs of the perfect cube here. So SOAP stands for same, opposite, always positive. So, same as the original expression, opposite, and then always positive. And then in factoring the denominator, again, we're going to have to go ahead and use the aside technique. When we use the aside technique, okay, we're asking ourselves, is this factorable? Well, the aside technique, the polynomial we will look at is x squared plus 3x plus 4. So looking for two numbers that multiply together to give us 4 and add together to give us 3. Unfortunately, there is none. So this polynomial is not factorable. Since this one's not factorable, it also means that this one is also not factorable. So unfortunately for us, this one does not factor, and hence nothing cancels out. Therefore, this expression of x cubed plus 1 all over 4x squared plus 3x plus 1 is in lowest terms. And the last example on this section, okay, will be x cubed minus 27 all over x squared minus 9. Okay? Again, the key here is going to be the factor. So factoring the numerator is a difference of cubes. So just like a sum of cubes, it will factor into a binomial times a trinomial. This will be x, 3, x squared, 3x, and 9. My signs will go same, opposite, always positive. X squared minus 9 is a difference of squares. That'll factor into x minus 3 and x plus 3. And as you can so very nicely see, the x minus 3's will go ahead and cancel out. This then leaves me x squared plus 3x plus 9 all over x plus 3. Now, on Blackboard, you will find a copy of the notes that I've just completed underneath this video. Feel free to go ahead and print them out, and if you would like to rewatch the video and add new notes to those additional notes, feel free to go ahead and do so. Also, there is a worksheet posted underneath the Assignments tab under Exam 4 Homework. If you would like to go ahead and start that this weekend, feel free to go ahead and do so. The solutions are right below it. I will, however, pass out a hard copy of it in class on Monday. Okay, so take a look at those. Make sure you're doing okay on this. If you have any questions, feel free to email me. Again, my email address is mdailey, D-A-I-L-E-Y, the number 1, @ccac.edu.